Hello, everyone. Welcome to the third and final day of this conference. As with the other days, we're going to have a series of talks. And I just know that on the right side of the user interface, you have a chat. There's also a Q&A section, and you can post questions there. I will monitor these questions, and I will ask them to the speaker at the end of their talk. And with that, I think I'll jump right in and introduce our first keynote speaker, well, our second keynote speaker of the conference. This is Guy van den Broek. He is an associate professor and Samueli Fellow at the Computer Science Department at UCLA. Many of you here will know his work on the Problock language while he was at Leuven. Today, he works on a range of topics which spans statistical relational learning, graphical models, lifted inference, and of course, probabilistic programming. His work has been recognized by Best Papers Awards at UAI, ILP, and KR. He's been the recipient of a number of other accolades, including the NSF Career Award, the Sloan Fellowship, and the Computers and Thoughts Award at HCAI 2019. We're delighted to have Guy here. Guy, if you're ready, you can unmute your camera and take it away. Let's see. So it appears that he has dropped off for a moment, maybe to reload his interface. I saw him say earlier that he couldn't hear my audio. So we're just going to wait a moment for him to rejoin. So I see that he is rejoining now, so we'll just give it another few moments.
Hello.
There we are.
Hey,
Guy, welcome. I believe if the technical issues are now resolved and you're ready to go, please take it away.
Thanks. So let me just start the presentation. Yeah, I have no idea what you just said, so I'm just assuming you said only nice things about me.
Guy van den Broek is a terrible researcher. We don't know why we have him at this conference.
Yeah, I was the fifth choice, of course. Yeah, no. So thanks for having me, and sorry for the little problem here. Yeah, I'm very honored to be here, and I guess I can start, I suppose. All right. So the talk that I wanted to give today is about how to go from probabilistic circuits to probabilistic programs, and also how to go back. And maybe that doesn't make sense right now. So let me maybe start with like a high-level motivation for why you should care about this particular topic. And I'll try to be a bit provocative, even though maybe for this audience it will not be provocative at all. So here's the provocative statement. Probabilistic graphical models are kind of the staple of how we do probabilistic AI. They've been around for many decades. And so the provocative statement is that graphical models that capture variable level dependencies or independencies, they're really a broken abstraction. And I think many of the people in the audience know this, and there's very simple examples to illustrate this fact. So for example, if you want to capture the distribution of a deck of cards as a graphical model, you'll have to introduce a node for every card in the deck. And the value would be, what is the type of the card? And then if you want to connect all of these different random variables together using edges to capture dependencies, you end up with this graphical model here. Everything's connected to everything. Okay. If you come from the statistical relational learning community, you're very familiar with this issue. If you have something like a Markov logic network and you try to interpret it as a graphical model that captures variable level independencies, then again, everything is completely connected. Even if you're from the probabilistic programming community, you're very familiar with this. And so here, I took an example that I stole from the Facebook people and about their new probabilistic programming language, the Bean Machine. I think they will give a presentation about it in an hour. And one of the observations here is that if you write this probabilistic program as a graphical model, then very quickly you run into the limitations of graphical models, because some of these dependencies here that are represented by edges, they only really exist in a certain context. And so this is where the graphical model formalism kind of fails. Okay, so let's try to come up with a better solution. By the way, if you hear a chainsaw outside of my office, that's because someone's cutting down a tree, so I apologize if there's extra noise. Okay, so maybe probabilistic graphical models are not exactly what we want here. And so what would be the alternative? And so what I'm trying to postulate here is that computational abstractions of distributions are kind of the modern alternative. So let's think of distributions as objects that are computed. And so the abstraction here is not, which variables depend on which other variables in a graph, but it's the structure of our program, of our computation, that actually gives us the high-level overview of what this distribution is actually doing. And now you're thinking, well, maybe you're rolling your eyes because this is something that you're all familiar with. You're all probabilistic programming researchers. And so, yes, I am, of course, talking about probabilistic programs. However, maybe to your surprise, I'm not exclusively talking about probabilistic programs. So there are other formalisms out there that follow this same philosophy of having a computational model of a distribution, and then doing, in some sense, better than what we could do with probabilistic graphical models 10, 20, 30 years ago. Okay, so what do I want to talk about today? Well, since you all know about probabilistic programs, maybe I will surprise you with some little tutorial about probabilistic circuits, and then also some overview of the recent work that my research lab has been doing on that topic. And then at the very end, I'll tell you how probabilistic programs and probabilistic circuits are related to each other. And then actually in maybe an hour, Stephen Holtzen will give a talk about his new probabilistic programming language, which will also make this connection much more clear. Okay. So on the agenda for the next half hour, what are probabilistic circuits? Why are they interesting? Why should you care? And what are the cool things you can do with them? And I want to start with this overview here. And so this is a subset of all of the probabilistic models you will find in the machine learning literature. And it's a huge mess, right? So there's kind of the classical ones, the ones that you got in your Introduction to AI textbook, things like naive Bayes. There's things like Bayesian networks here, right? So these are some of the classics. But then there's also variational autoencoders, which are really popular today. GANs, of course. GANs have to appear in every talk. Autoregressive flows. There's all sorts of different deep generative models here, and also the classical graphical models, and then a whole bunch of stuff that you may never have heard of, but I will explain some of them. And so the question is, how do I look at this picture and make sense of this alphabet soup? And well, maybe the first thing to note is that some of these models are tractable and some of them are intractable. So what does this mean? If I have a naive Bayes model, let's say, then I want to compute the probability of my class variable given my features. I can do this very efficiently in linear time in the size of my naive Bayes model. Some of these other models have similar properties, thin junction trees, tree-shaped Bayesian networks. And so these we will all call tractable. And there's a few acronyms here that you may not know, but they will make an appearance in a few minutes. And then on the other side, we have the intractable models. And so GANs are in some sense the worst offender here. They don't even allow you to really compute any probability in your distribution the way you would like to in a probabilistic program, for instance, or in a Bayesian network, because there is no actual explicit probability of anything. There is no likelihood function. Some other models have an explicit likelihood function, like the variational autoencoder, but then the problem is that computing it exactly is completely intractable, and you can only approximate it, right? And so this is an important distinction that I'd like to make between tractable and intractable models. Okay, so let's zoom in a little bit into these tractable models, because maybe you're familiar with GANs and variational autoencoders, but these tractable models are maybe less familiar to you. And I will just give a very quick tour of all of the different models that have appeared in the literature in the last 20 years. And I will just not explain them and just kind of flash a picture in front of you. So this is a tree-shaped Bayesian network. It's a tractable model, and you learned about it in your kind of Bayesian networks Intro to AI lecture. This here is an arithmetic circuit, very popular in the Bayesian network community. We have a sum product network, very popular in the machine learning community. This is a probabilistic sentential decision diagram, an AND/OR graph, a cut set network, a probabilistic decision graph, a DDNNF, a BDD, and a SDD for doing weighted model counting. And so why am I showing you all of these things? Well, all of these different models have been proposed as like modern ways of representing probability distributions, but they're all slightly different, mostly in their syntax, but also in their properties. And so each of these models has a reason to exist. They all have kind of important new contributions they make to the field. But the issue is that, yeah, it's impossible to really make sense of this literature. And, you know, hence the quote, every talk needs a joke, and a literature overview slide not necessarily distinct. All right, so what is our goal here? So the goal of probabilistic circuits is to say that all of these different things, you don't really have to understand them one by one. All you need to do is understand this unifying framework that kind of explains all of these different machine learning models and also explains what they are able to do, what they're able to compute efficiently, what they're not able to do, and what the trade-offs are. And so this is the framework of probabilistic circuits to explain all these things. Okay, so now I would like to just give a mini 6-slide tutorial on what are these probabilistic circuits and why are they tractable. It will be a little bit high level, but I hope I can convey the key points here. So what you see here is a probabilistic circuit. It's a tiny one that fits on a slide, and it really looks exactly like a neural network, where you have your input layer, which is shown in gray here, and then you have your output neuron, which is the root here of this directed acyclic graph. Then all of these nodes in the middle are little computational units, just like you would in a neural network. Okay, so no surprises there. However, we'll have to assume a few extra things about what these neurons are actually doing. And the first thing that you'll have to assume is that these inputs here, they're not just features, but they are little distributions in their own right. So these input nodes, they could be a univariate Gaussian, maybe some Dirichlet, some Laplace, maybe a Bernoulli or some categorical random variable, but it should be a very simple little distribution that you know how to handle, that is not posing you any computational challenges, right? And so, for example, here, this input distribution here says the variable x2 has a probability of 100% to be set to 1 and probability 0 of being set to 0, right? So this is a little indicator function, which is in some sense the most trivial distribution you can ever think of. Okay, but they could be Gaussian, continuous, could be really anything that you're willing to plug in here. All right, so then what in this large computation graph are all of these other nodes doing? Well, there's two types of other nodes. One is a product node, shown here in gray. And the product node serves as a way to take two distributions that are talking about different sets of random variables and then combine them into one larger distribution. And so that's the idea of factorization, right? You take some component distributions that are talking about different things and you multiply them together to get a larger joint distribution. All right, so that's a very simple operator to get a slightly epsilon more complicated distribution out of what you started with. The next type of node, and the only remaining type of node here, is a sum node. And a sum node is slightly more interesting. It represents a mixture model. So what you do is you take smaller probabilistic circuits, which are the inputs to your neuron, and you combine them together using some weighted average. You're creating a small mixture model over all of these components, and every component, of course, has a weight associated with it, and that weight is here annotated on the edges of the inputs. Okay, so this is kind of like a neuron that combines two distributions into one. Of course, this one distribution is slightly more complex because it mixes together these two trivial distributions. And so, for example, if this were a Gaussian and this were another Gaussian, then over here you would get a mixture of Gaussians, which is slightly more complex and slightly more interesting. Okay, and that's really all there is to it. If you now just build a probabilistic circuit like this that has 100,000 or 1,000,000 edges and parameters, then you have a very large probability distribution. Okay, so why would you care about this? Why is this an interesting representation? Well, the whole reason why we cared about these things is because they give us tractable inference. And if you work on probabilistic programming, you know that it's very, very difficult to achieve tractability, right? There's just certain programs that it's very, very hard to get accurate estimates of your conditional marginals, for example, or any kind of query you may have. Well, it turns out that's not an issue in these representations. And I'll just give you one example, which is I want to compute a marginal probability in this distribution. And I'll also explain to you how that is tractable if you are willing to assume two simple properties of this probabilistic circuit. And so I'll try to kind of give the intuition of why this is possible. Okay, so first thing you need to do is assume smoothness. And this is a very natural property. What this really means is that when I have a mixture model, like the sum node is mixing these two smaller distributions together, then those two smaller distributions, they have to have the same random variables in them. And that makes sense, right? You cannot create a mixture of Gaussians where one Gaussian talks about the age of the person and the other Gaussian is about the height of the person. You cannot mix those two things together. And so that's the property of smoothness. Once you have the smoothness property, it becomes really easy to compute an integral. And computing an integral is really what you need to do when you want to do a marginal probability inference. Because I have an integral of a sum, right? This mixture model here is a sum. The sum is weighted, and an integral of a weighted sum is just a weighted sum of the integrals. And so now we can make progress. If I want to do an integration here in my distribution, which is represented by this node, all I really need to do is do an integration computation here in these two children, these two inputs, and then compute the weighted average. Okay, and so that's the reason why in a probabilistic circuit, you can push your integration one level down. But we haven't solved the problem yet, because next we have this multiplication node, and we don't really know how to compute an integral of some product, right? A product of two distributions that are factorized. And so here we'll have to assume the second property of our probabilistic circuit, and it's called decomposability. So decomposability says that in any kind of factorized distribution, the individual factors, they have to be independent of each other. So x, y, and z here are disjoint sets of variables, and I can multiply them together to get a decomposable product here. And if you have this property, then again, computing an integral becomes easy, because integrating over x, y, and z separately can just be done in each of these little distributions separately, and then you can multiply their results. Okay, and now we're done, right? So now we pushed our integration problem through the sum nodes, through the product nodes, and eventually we reach these very simple distributions that are our inputs here. And so here we have a Gaussian or a Bernoulli or something simple that we like, and here we assume that we can efficiently compute all of these integrals. Okay, let me give you one example of how this works, and so then I hope you'll be convinced that these models are actually tractable, and you can compute things in them that you couldn't compute in a Bayesian network or in a VAE or in probabilistic programming languages. So here's the example. I want to compute the probability that x2 has some value and that x4 has some other value. What does this mean? Well, there's other variables x1 and x3 that are missing from this marginal inference computation, and so I have to integrate them out, right? So I have to integrate over x1 and x3. Because of what I explained on the previous slides, I can just push my integration problem to the leaves of my probabilistic circuit. If the leaf is a variable that I need to integrate over, like x1, then I get my integral. And so the integral here is 1, of course. All of this probability mass sums to 1. For the variables that I have a value that I observe, like x2 and x4, I just have to plug in the likelihood in this little simple distribution. And now I'm really done. I just need to take a product of a sum of a product of a sum, and I get my marginal probability here at the output. Okay, so I hope this made sense. And I hope you're still hearing me, since I have no feedback loop, so I'll just keep going. The point of this exercise is to convince you that, yeah, there are really difficult computational questions that become easy once you have a probabilistic circuit with the right properties, in this case, smoothness and decomposability. But what I just explained to you is just these two check marks here in this larger table. And there's all sorts of other things you might want to know about your distribution. You want to maybe compute conditional queries, moments, means, map inference, marginal map inference, compute entropies, all sorts of divergences, expectations of other functions. And so it turns out that for all of these tasks you want to compute, there is a circuit that does it for you. And all you need to know is whether your circuit has the properties that make these queries tractable or not. And so this is the landscape of probabilistic circuits. And so I hope that I was able to convince you that, yeah, these things are tractable, but there's also a spectrum to it, right? So depending on what you want to do, some things are easier than others. And so something very, very simple like a naive Bayes model or a fully factorized distribution, you can compute almost anything in. Something very, very intractable like a GAN is you cannot even compute a likelihood in. And so there's a whole spectrum in between, which is kind of covered by the table I showed you on the previous slide. Okay. Now, in future, if you have this huge literature on these probabilistic generative models, all you really need to know is what are the properties of the probabilistic circuits version of all of these different things, and it all makes sense to you. There's maybe one more remaining question that you have. It's maybe related to the observation that, yeah, sure, naive Bayes is tractable, but why should I care? Naive Bayes is such a really dumb distribution that I don't really care to fit my data with a naive Bayes model or a tree-shaped Bayesian network. And so maybe the intuition that you had before this talk is that, yeah, sure, I can come up with some deep generative model that is tractable, but it's not actually going to be very expressive, right? If I'm able to compute, let's say, a marginal probability efficiently, then surely the model is so trivial that I shouldn't care about it. And so here I want to convince you that this intuition is false. So there are these types of probabilistic circuits that are actually both expressive and tractable at the same time. And the way that I'll try to convince you of this fact is by showing you some experiments. And of course, this is not on data sets of the size of ImageNet, but these are reasonably large data sets with tens of thousands of examples, hundreds to thousands of features, right? Of how well do I fit my data? How well can I actually fit a density to this data? And what we compare here is the best probabilistic circuit model to the best Bayesian network learner with advanced context-specific CPTs, and then two deep generative models, so some autoregressive models and a variational autoencoder. And I think the summary of this slide is that depending on the data set, either the probabilistic circuit gives you the highest likelihood. Sometimes even the classical Bayesian networks do well, which is maybe also a surprise. Sometimes one of the deep generative models does well. But it's really very close, and it kind of depends. And this is surprising. Why? Because all of these models, these Bayesian networks and the deep generative models, they're all intractable. They won't allow you to compute a marginal probability. All of these circuits, they are tractable. You can compute any marginal or conditional probability in them in time linear in the size of your circuit just by evaluating the circuit in the way that I showed you a couple slides ago, right? So here the story is that you can get tractability without really too much of a compromise. And so you should really think of these tractable models as also being very expressive. All right. So I didn't really tell you about all of these acronyms. I'll briefly mention again things like sum product networks and arithmetic circuits, which are perhaps most famous. So all of these really live up here. They're both tractable and expressive. And in that sense, they're very different from your classical tractable models like tree-shaped Bayesian networks. And then other expressive models are our classical deep generative models, but they're completely intractable for almost any kind of query you may want to ask. And if you want to understand these things, I mean, for sure, read the papers, but maybe if you understand what a probabilistic circuit is and why it's tractable, then you also understand what all of these things are doing. Okay, so this was a very quick tutorial just to convince you of a few key observations about probabilistic circuits. If you want to know more, then there's this tutorial that we gave at ECML with Yu-Cheng Choi, Robert Pejas, and Antonio Vergari. And so you can watch this tutorial. It's 3 hours. It goes into other types of queries, how to learn the parameters and the structure of these things from data, and some more theoretical properties. So there's a lot of good stuff here. If you prefer to read a very nice overview paper written by Yujang and Antonio, then there is a preview on my website where you can just download this paper, and it kind of explains the whole framework in a very intuitive way. If you're someone who just likes to look at code and doesn't want to read anything, you may also want to try out our Julia library, which is for working with probabilistic circuits, doing inference and learning. And just to show you that these things are actually very, very scalable, I'm going to, here in this pseudocode, just tell you, you load some circuit structure, which you could have learned from data, could come from anywhere. You have maybe a couple 10,000 examples, a couple 100,000 parameters or edges in your circuit, and in 63 milliseconds, you can estimate the maximum likelihood parameters exactly of this model. Why? Because it's tractable, right? So if you care about learning, then you should also care about probabilistic circuits. And so please check out all of this code here. Okay. So this kind of ends my mini tutorial on probabilistic circuits, and I hope things are clear. And for the remainder of my talk, which is not very long, maybe 10 minutes, I will try to tell you what my research lab has been doing around probabilistic circuits and kind of the new things we're trying to develop. And so this will be kind of a whirlwind tour of a bunch of different topics, just to give you some pointers. Okay, so the first question that I was really passionate about maybe a year ago is, these probabilistic circuits, they kind of explain why everything that I know to be tractable is tractable. So are these probabilistic circuits really a universal tractable probabilistic model? Anytime I have a model that I can compute something exactly in, is it always going to be a probabilistic circuit? And for a long time, I thought the answer was yes, that this was really the language of all tractability. But then my student Honghua and Stephen found a counterexample. So there are still certain distributions that are popular in machine learning, things like determinantal point processes, for which we don't have a probabilistic circuit representation. And so therefore, when I told you every single tractable model is just a probabilistic circuit, this here is the exception. And so I would encourage you to read this UAI paper from this year, where we kind of go through why these particular DPP distributions cannot be represented as probabilistic circuits. And maybe I'll give you a quick answer. So these DPPs, what they do is they tell you that some likelihood or marginal probability can be computed by taking a sub matrix of some matrix that is my model and computing the determinant, the subdeterminant of this matrix. And so computing a determinant can be done efficiently. So this is a tractable model. This is how I do inference. However, you won't be able to do so with the probabilistic circuits that we're currently aware of. And then so a major question here is, these are almost universal tractable languages, and we're trying to develop a model that really captures all known types of tractability of this form. Okay, so that's the question of the representation. Another question is, what can you do with these models? And so here I want to quickly motivate some of the work we're doing, and I want to motivate it using this AI dilemma. And this is like a very simplified way people think about AI. There's the old way of doing things, which is logic-based, reasoning-based, model-based, and it's good at extrapolation and kind of cognitive tasks. And it's really good at some things, but it's also brittle because it doesn't know how to deal with uncertainty. And so this is something everyone's familiar with as the limitation of classical AI. What is maybe more surprising is what I would describe as the limitations of kind of the modern machine learning approach to AI. And so we know that this is also really good and effective at dealing with kind of perception task, interpolation, model-free kind of reasoning. But it's also really brittle. And this is something we came to realize in the last few years. Why is it brittle? Because all of these issues come up about bias, fairness, explainability, adversarial attacks, unknown unknowns, issues with calibration, not being able to verify behavior, missingness, data distribution shift. So the list goes on and on and on of all of the issues that arise with just end-to-end black box supervised machine learning. And it's all because these approaches fail to really understand the world and how it works. And they've just been trained to just do one thing without really having a model of the world. And so here I think that both probabilistic programs and probabilistic circuits are the answer. And so what we're trying to do is come up with some new synthesis of this pure learning approach with the classical way of doing reasoning about models, and specifically probabilistic models of the world. And I'll just give you a very quick preview of what we're doing in algorithmic fairness, in explainability, and in dealing with missing features in machine learning models. And so this is going to be just a little survey of how probabilistic world models are the solution to the problems of end-to-end black box machine learning. All right. Here's the problem. I have a data set which is complete. It has, let's say, medical tests for all my patients. It has sensor readings for all my sensors. And now I'm training a classifier, some random forest or some neural network. It doesn't really matter. But at prediction time, suddenly one of my tests becomes unavailable or too expensive. One of my sensors fails. And so now my predictive model becomes completely useless because my neural network assumes that it has access to this feature and it doesn't really know how to deal with the missingness of this feature. And so the solution that we are looking at is called expected predictions. And so here the idea is that I have some function f, which could be my decision tree, my neural network, and I observe the features xo, observed features, but then there's a bunch of features xm that are missing, and I would still like to get a prediction out of my model. And so the way that we'll do this is by having a probabilistic model of the world, just like I said on the previous slide, that takes these observed features as input and then has a posterior distribution on the missing features. And so we will compute the expectation of this classifier with respect to this distribution, which tells us what are realistic inputs to my classifier, what is the data distribution of my features. Okay, and this seems kind of like a crazy task because this is probabilistic inference, right? You're doing probabilistic inference about a function that is, let's say, a random forest, right? So this seems crazy because it seems impossible. Well, it's actually possible and it works really well, even if you have a trivial distribution and a trivial function. So here you see some kind of early experiments with this approach where we use a naive Bayes model to take an expectation of a logistic regression model. And we compare it against what really everyone in the sciences is doing, which is imputation to solve this problem. And so even for this very, very simple probabilistic world model, which is naive Bayes, this is possibly the dumbest model we could have used. Already there, the accuracies are way higher for prediction with missing data than the imputation techniques that people are using. But of course, our goal is not to just have a dumb naive Bayes model as our probabilistic world model. We want to use these tractable probabilistic circuits in order to get some really efficient expectations. And it turns out that, yes, you can do this. So here you see just another syntax of a probabilistic circuit. This is a way that we represent classifiers, tree-based classifiers, for example. And so here, in almost the same way that I explained to you how you can compute marginals by breaking up an integration into pieces, also here you can take an expectation for your expected prediction task and break it into pieces and recursively solve it on the circuit structure efficiently in time that is polynomial in the size of these probabilistic circuits. Okay. If you then again compare to what people do today, which is imputation, including multiple imputation techniques like mice. Mice is probably what everyone is using in like psychology for dealing with imputation. Again, these expected predictions get you the highest accuracies and the lowest root mean squared errors. Okay, and so this is a great example of how probabilistic world models can really help solve the problems of just supervised machine learning. Okay, moving on to the next example is how do I deal with algorithmic fairness? Well, if you can compute expectations, you can also do some really interesting things like asking in the distribution over my people that are my customers, how does the predicted insurance price change between female and male applicants for insurance? And then you see that that women are paying a higher insurance price in this particular predictive model for insurance prices. Okay. And so you can really start to ask questions about algorithmic fairness here. And if you really push this to the limit, you can actually try to solve some algorithmic fairness problems by learning a probabilistic circuit. And so what we did in this paper here is to learn a classifier that doesn't really treat the labels that it's given as the true labels, but it treats them as unfair labels that maybe incorporate some racist or sexist bias or whatever bias there is. And what we'd like to figure out is what is the fair decision that was the actual underlying latent variable, such that it's independent of the sensitive attributes. So it doesn't take, for example, race into account, but it also explains the observed unfair decisions. And so this is a latent variable model. However, it's a very complicated one, and you need to really fit the data, and you also want to be tractable, right? Because you have to model this data in a way that is solving. You need to solve EM. It's intractable. So the solution here is to learn again a probabilistic circuit. And then you see if you. Great. Yeah. So I think I'll be done in 3 minutes, hopefully. Awesome. So if you use this latent variable probabilistic circuit model, then you see that you're more accurate while also being less discriminating based on the protected attributes. Okay, last example of how probabilistic world models can solve machine learning issues is in explainability. And so here we have a line of work which is trying to explain instances of classification, local explanations. So why were these two MNIST images classified the way they were by our machine learning model? And so maybe you don't think of this as a problem where you need a distribution at all, but it turns out that yes, it is very intuitive to think about this problem as a problem of the data distribution. So specifically what you want is something that is a probabilistically sufficient explanation. So what does it mean? It means that whatever the explanation will be, it will give us a little bit of information, and that little bit of information should be sufficient under the data distribution to make the prediction that the model made, right? So what are really the essential pieces of information that in the data distribution will cause me to classify this image the way that I did? And you also want this to be simple. And so here's then some output of this model. This is an explanation for why this was classified as a 5, and the gray pixels are the ones that are marginalized out, they're unknown. And you can kind of see a 5 here. This is an explanation for why this was classified as a 3, because you see that really these pixels here kind of represent a 3, and in my data distribution, this information is enough for the model to start concluding that the image is a 3, even though it was really a 5. All right, so that's a very quick overview of how you can use these probabilistic circuits to solve some of these problems. Now, to wrap up for 1 or 2 more minutes, I promised you something about probabilistic programs, right? Probabilistic programs were the other type of model that had this computational abstraction. And so here, I want to point you at the talk that Stephen Holson is going to give in 25 minutes about DICE, which is our new probabilistic programming language for discrete probabilistic programs. And why is this connected to probabilistic circuit? Well, it turns out that the way that you do inference in these programs is by compiling them through some pipeline into a probabilistic circuit, right? You essentially convert your intractable probabilistic program, where computing marginals is sharply hard and you don't really know how to do it. You exploit the structure in the program in order to get a compact probabilistic circuit, and once you have the probabilistic circuit, you just run the algorithm that I showed you, and it allows you to compute the marginals you care about. Okay, and so this is really the state of the art for discrete probabilistic program inference. It's also an approach taken by, for example, Broeck in probabilistic logic programming, and it's really, really fast. Okay, so conclusions of my talk. I think we are already in the age of computational abstractions of distributions. Why? Because we already have 2 examples, probabilistic circuits and probabilistic programs, and both are getting increasingly popular. Probabilistic circuits you can think of as a type of deep generative model, a deep probabilistic model, however, one that is tractable. And so one that allows you to understand what types of queries you can compute and which ones you cannot. And then probabilistic programs, of course, I don't have to convince you, is the new type of probabilistic knowledge representation language. And these are very closely related because you can compile your probabilistic programs into your probabilistic circuits for inference. And this is not just a cute exercise. This is the state-of-the-art way of getting your probabilities. So I should then thank you, and also thank my students and postdocs who did the real work. A whole bunch of them are graduating. And they're actually going on the academic job market. And so specifically, Yitao Liang and Antonio Vergari, who worked on probabilistic circuits and did a lot of seminal work there, they're on the academic job market. So feel free to reach out if you're interested in talking to them, for example. All right, thanks.
I'll just briefly applaud for the audience. So we do have a lot of questions, actually, and we're a little bit short on time. So I will pick off the most popular questions, and then I'll encourage people whose question we didn't get to follow up with you. And I'll wrap maybe two questions together. One is from Neymar Aurora, and one is from Michael Tingley. And the first question is, how user-friendly are probabilistic circuits for purpose of knowledge representation? And then the second question is, how much human intuition and engineering is necessary to design one of these probabilistic circuits? And is it possible to discover the structure of these circuits automatically?
Oh, so these are all great questions. So I'll try to give very short answers. So how human readable are these probabilistic circuits? They're not, right? So they will have maybe 10 million parameters. They're exactly like a neural network, exactly like a VAE, except they're better in the sense of being tractable. So the way that you would model them is just say, I want 25 layers, and I want, it's just like you use neural networks. So that's why I think probabilistic programming is important in conjunction with probabilistic circuits, because probabilistic programs will give you the human readable structure, and then you can still mix and match them and learn the probabilistic circuit given the probabilistic program structure, and so on and so on. So that was one question. I'm not sure if I remember the others.
Yes, I guess the other one was about how user-friendly it is for knowledge representation, which I think you've more or less answered.
which I answered. Oh, one of the questions was, how do you learn them, the structures? So I would really encourage you to look at the tutorial where Robert Pejas speaks for an hour about how do you get these structures, how do you estimate the parameters, what is maximum likelihood learning in this context. And so there's all sorts of algorithms there that work really well.
Great. And so then I'll ask one more question, which is from Vikash, which is, have you identified classes of generative processes with dynamic memory allocation or control flow, for example, PCFGs, that still admit smooth, decomposable, tractable representations?
That's a great question, right? So at some level, if you, let's say, have a open universe model like Broeck, then of course a probabilistic circuit that is not open universe is not going to solve it, right? So you need to maybe think of some extensions of this basic framework. Things like PCFGs, though, they have compact probabilistic circuits. So I know this because, for example, Angelika Kimmich's PhD thesis exactly explains how PCFGs can be turned into probabilistic BDTs. So those are already covered.
All right, I was going to say let's thank the speaker, but I guess the audience can't thank the speaker except in chat. Thank you so much, Guy, for joining us. I'm going to ask the next speaker